Assalamualaikum and hello again everyone. In this video, first we're going to talk about something called conditional probability. The idea with the conditional probability is that we want to figure out the probability of something given that we have some other piece of information. The other piece of information that we can bring to the table that will influence the probability of whatever it is that we are investigating. Now, we can sort of visualize how this is going to work by using a Venn diagram. So, a Venn diagram listing the entire universe of possibilities in the sample space, and then within the entire universe, we can have probability of an event A occurring, and we can also have a probability of some event B occurring. Well, if we're looking at this sort of conditional probability, it's like where this event B is occurring. I'm assuming that event B occurs here. And then what I'm really interested in is what is the probability of this event A occurring given that I'm in this event B and this event B has occurred, in which case I'm really interested in this intersection here. In other words, it's about the ratio of the probability of the intersection, the red area, to the probability of B occurring, the yellow area. Now, the way we write this down is with the following notation. We're going to refer to the probability of B given A denoted by PB vertical bar A. So, this vertical bar that we have here is referred to as given, and what it means is that the probability of B, the thing that we want or looking for, given that we have this other piece of information, given that we know that this event A is occurred. So, we're going to have some formula for how we're going to compute this. It's a quotation of two things. It's the probability that we have both the event A and event B at the same time. So, it's written as intersection. It means the probability of B and A all divided by the probability of just A. But we have to do one restriction if we need to put it this up mathematically. This formula won't work if the probability of event A is 0, since we would run into a 0 over 0 issue. Let's start with a simple example where we have a sample space from 0 to 6. Then we have a reduced sample space, event A and B. Next, what is the probability that A and B occurs? So, 1 and 3. Well, what's the probability of B occurring given A? So, A is the condition. So, based on the formula given, the probability that A and B occurs here divided by all the possible ways that A occurs. So, the probability of event A and B occurs at the same time is equals to 2 over 7. Then the probability of event A is 3 over 7. So, PB given A is 2 over 7 divided by 3 over 7 equals to 2 over 3. Let's work through another example. Consider the population of adults in a small town categorized according to gender and employment status. Let's look for the probability of a man given that he is employed. Before going through the formula, let's work through this one quickly. So let M, a man is chosen, and E, the one chosen is employed. So for the total possibilities of the sample space is equals to 900, and then PE, the employment status of an adult, is equals to 600 over 900, and the possibilities of having a man with an employment status record at the same time is male employed, therefore is equals to 460 over 900. Then, according to the formula, to find the probability of a man chosen that he is employed, we need PE intersection with M over PE, which is equals to PE intersection with M equals to 460 equals to 900 and equals to 23 over 45, where we have PE, a person chosen is employed, equals to 600 over 900, which is equals to 2 over 3. Then let's PE intersection with M be the numerator and PE be the denominator, and the answer is equals to 23 over 30. In this next example, we have the probability that a regularly scheduled flight departs, PD equals to 0.83, and then we have the probability that it arrives, depart, and this one is arrives, PA equals to 0.82, and the probability that it departs and arrive on time is PD intersection with A equals to 0.78. So the first question is to find the probability that a plane arrives, PA, on time given that it departs on time. So to write this is PA given D. And the second is to find the probability that a plane depart, PD, given it's arrive on time, PD given A. So for the first one, PA given D equals to PD intersection of A over PD, which is equals to 0.94, and the second one, PD given A equals to PD intersection with A over PA equals to 0.95. In conclusion, that we can see that the denominator is always the given condition. Event A is independent of B if the conditional probability of A given B is the same as the unconditional probability of A. That is, they are independent if PA given B equals to PA or PB given A equals to PB. Otherwise, A and B are dependent. In the die toss example, PA given B is equal to PA intersection with B, which is here we have 2 over 6 and PB equals to 4 over 6. So PA given B equals to 1 over 2, which is also equivalent to PA. Therefore, A and B are independent. Next, using the same die toss example with the same sample space but different elements for event A and B, here PA equals to 2 over 6, which is 1 over 3. PB is 4 over 6, which is 2 over 3. And A with B, A and B equals to 1 over 6. So PA given B equals to 1 over 4, which is not equal to PA. Therefore, A and B are not independent. Multiplying the formula in definition 210 by PA, we obtain the following important multiplicative rule or product rule, which enable us to calculate the probability that two events will both occur. This theorem 210 is simply a rearrangement of the conditional probability. Thus, the probability that A and B occur is equal to the probability that A occurs multiplied by the conditional probability that B occurs given that A occurs. Since the event A with B and B with A are equivalent, it follows from this theorem we can also write that PA with B and B equals to PB and A, which is also equals to PB multiply with PA given B. In other words, it does not matter which event is referred to as A and which event is referred to as B. Let's work on example 2.37. We have one bag with 4 white balls and 3 blacks, and then a second bag contains 3 white plus 5 blacks, and then one ball is drawn from the first bag and placed in the second bag. What is the probability that a ball now drawn from the second bag is black? Okay, first let's name black as B and W for white, and 1 and 2 is the number of the first bag and second bag. Okay, let's see the tree diagram for the problem. So for bag 1, we have 4W and 3B, and once we have drawn black balls from bag 1, the probability is 3 over 7. As for white, it's 4 over 7. And then we add this black to second bag, becomes 6B and 3 whites. Therefore, we have the probability of having black is 6 over 9, and probability of having white is 3 over 9. It goes the same for if we add whites to the second bag, whites become 4 and plus 5 blacks. And then the probability of having black for this bag, it becomes 5 over 9, and this one is become 4 over 9. Okay, and then to have event B1 and B2, we just apply the multiplicative rules. 3 over 7 times 6 over 9. It goes the same with other events until W1 and W2. Here what we are interested with is the probability of having a black ball from the second bag. So look for B2. Okay, so these are the two probability that we have to look for. Therefore, from the formula we can apply that we are looking for B1 and B2 or W1 and B2 at the same time. So these two probabilities is equals to PB1 intersection with B2 plus W1 intersection with B2. Okay, and then we gonna solve it using the theorem 210. We will get 3 over 7 times 6 over 9 plus 4 over 7 times 5 over 9, and the answer is 38 over 63. Theorem 2.11 suggested that if we have two independent events, A and B, we can obtain the probability of that two independent events occurs at the same time with simply the product of their individual event. Like in this example, we have a small town has one fire engine and one ambulance for emergencies. The probability of having fire engine available when needed is 0.98, and then for the ambulance is 0.92. In the event of any injury resulting from a burning building, find the probability that both the ambulance and fire engine will be available. Okay, to find the probability that both the ambulance and the fire engine will be available is equals to the product of PA and PB, which is equals to 0.9016. To close the conditional probability, independence and the product rule topic, I'll leave you with some of the exercise questions for you to try later. One of the most interesting topics in probability is Bayes' theorem, and it's nothing but an application of conditional probability. Previously, in conditional probability, we have seen PA given B equals to PA intersection B divided by PB, or PB given A equals to PB and A over PA. Here what we have is PA intersection with B is the same thing with PB intersection with A. Okay, as both events occurs at the same time. Therefore, if we move this up here, we can have P A section with B equals to PA times PB given A over PB. Or we have PB given A equals to PB times PA given B over PA. Here is the interesting parts about Bayes' theorem, because sometimes in some problems it's easier for us to find probability of A given B, or sometimes it's easier for us to find the probability B given A. Therefore, this formula becomes very helpful and handy at certain cases of statistics problem. Alright, so let's go over an example 2.41. In a certain car assembly plant, there are 3 machines, namely B1, B2 and B3, with a certain productivity percentage around 30%, 45% and 25% respectively. Also, for each machine, there are certain percentage of defectivity of the product with 2%, 3% and 2% for B1, B2 and B3 respectively. Now, suppose that a finished product is randomly selected. What is the probability that the car selected is defective? Consider the following events. Event A, the product is defective, and then B1, the productivity percentage for machine 1, machine 2, B2 and machine 3, B3. Referring to the tree diagram, we find that 3 branches of probabilities, B1, B2 and B3. Then we have PA given B1, PA given B2 and PA given B3. So PB1 times PA given B1 equals to 0.006 and PB2 times PA given B2 equals to 0.0135, and then PB3 times PA given B3 equals to 0.005. Again, referring to Bayes' theorem, if the events B1, B2 or until Bk constitute a partition of the sample space S such that PBI is not equals to 0, for I equals to 1, 2 until k, then for any event A of S, PA equals to the summation of the product PBI times PA given BI. Then we can compute PA equals to PB1 times PA given B1 plus PB2 times PA given B2 plus PB3 times PA given B3. And it will lead to 0.006 plus 0.0135 plus 0.005 equals to 0.0245. Using Bayes' rule, a statistical methodology called the Bayesian approach has attracted a lot of attention in applications. We have come to the end of Chapter 2. This chapter contains the fundamental definition, rules and theorems that provide a foundation that renders probability an important tool for evaluating scientific and engineering systems. The evaluations are often in the form of probability computations, as is illustrated in examples and exercises. Concepts such as independent, conditional probability, Bayes' rule, and others tend to mesh nicely to solve practical problems in which the bottom line is to produce a probability value.